Yeah, so we have, let me open up a rendering of, you can totally do that too. They take a little bit longer. Just the processing of it takes a little bit longer. Actually, I think I can probably do it in 10 minutes. Yeah, so they definitely have those. We've got, I don't think there's a plugin yet that basically makes so NetFab, what's it called? N-topology does really good, it's not stochaic, but basically randomized structures like bone structures going through stuff. Stochastic, something like that, structures. But it's N-topology is the software. Currently their beta is free. Not their beta, the trial is free, but the resolution is low enough that like you can't, if I wanted to make a bone structure, I have to buy it. And so, but that's another one of the great ones. There's, what is it? Magix even has some infills, and you can do randomizing infills. I wrote a script that did Patrick Dunn, quick cast bracket. Not that one. I still don't have one. But I basically made this bracket, and we infilled it with a bone structure very quickly. So this was a combination of both topology optimization and basically infilling structures. So this was like we basically optimized the outside of the surface using solid thinking. And then then you get a solid block of material, which is sometimes great, sometimes not. Really I think since we know from hollow pipes that most of the forces on the object are basically exerted along the outside of the surface. And the inside of the object doesn't really have any forces exerted along it in particular cases. In this one, this was and I wish I had the rendering up here. But we definitely did it's probably on my hard drive. But we definitely basically combined different areas of things, like optimize the topology and then see how light you can make the object using a standard lattice infill. And then it was let's make a bone structure. And I basically killed my computer at a certain point when I was this works well at so a lot of times I will develop something at a very low resolution, not rendering, but I'll make sure it works with a combination of 10 pipes. And then at the very end, I'll be now I'll make it 100 million pipes and I'm going to go to sleep. And then the next morning I wake up and it either has exploded or I'll be done. And so that's definitely refine it at a really low resolution. And then when you're pretty confident and you know it's going to work, then you just change that number from 10 to 100. And then it'll take 100 times longer now. But it might work. I've done whole buildings like that where I designed it a 1/4 of the building and then went apply and then left for 2 days and came back and the building was done. Floor plans and everything, but it was just done through the right application of parametric software. And so you can save a lot of time, or at least a lot of sweat and tears and blood and tears, sitting there for 12 hours sitting here clicking on things. If I can parameterize it correctly and then just hit enter, it should apply across the board evenly, hopefully, or at least if you did it right, it should work. Does anyone else? We have 7 minutes left.
You mentioned conventional manufacturing.
Mm-hmm.
Who runs it?
So the website is run by my boss, Patrick Dunn, who is the vice president of advanced applications at 3D Systems. And he sort of pioneered the design for additive manufacturing back in the early 2000s. I think he started working in the industry in '98. And he was one of the first industrial design, I think he's an industrial design engineer or something along that category, to come into the field and was no, you can stop making these really simple, boring shapes or just literally printing your standard CAD files that you would CNC, and you're you can actually make really interesting shapes. They're not shapes, but really useful shapes. And now that we can print final products, and it's not just prototyping, where before, if you're printing a prototype, other than maybe saving you some money on the prototype, an infill lattice structure isn't very useful because you can't injection mold that. There's no point in being able to do it, other than maybe making your prototype lighter. But if I can actually print the final object with that lattice structure, like the spinal fusion cages, or I think I've got an image here of presentation. Like this, for instance. This was done through Autodesk's Within software. And so it's just literally a lattice fill structure. There's nothing smart or parametric about that lattice infill structure. It's just, it could be hexagons or diamonds. In this case, it's a random, pseudo-random infill. But here, let me make it big and full screen for you guys, or bigger. But see if you notice actually around around this area, that's a pretty low res file. I can see the flat, like whoever exported that didn't probably export it at not the correct resolution, but maybe that's what they wanted. Maybe the whole file was too heavy because of this infill. But that was definitely, I forgot where we were going with this. But this is that structure. Random, yes. You can totally do random. What else is there? Oh, this was an example of so this is a duct that someone CAD modeled for, it was to be originally stamped out in aluminum or steel or something like that, and it's this big in diameter. It's a giant box fan. And someone sent us the file and was like, print it. And so they just literally stuck the file in the printer and went go. And when they pulled it out, it warped, because it wasn't designed to be printed, it was designed to be stamped out of metal. And so this is an example of like at first they were like, oh, project's over, and they were really trying to basically reduce the cost of welding all of these things together, like having a whole team of people weld it. They would love to just pull these off in the machine. And so they were like, how do you basically make this better? Or what would be an example of something we could show to our designers to be like, how do you inspire them to basically make them better, or make the part better and not warp like this? And so this was what we made, which we just printed, and it actually didn't warp at all. And we basically turned these panels and that really thick, or these really thin, flat cross sections into arches. And the arches won't warp, basically. A big flat sheet of plastic has a tendency to warp because of different thermal stresses, but if it's a nice arch, it contains those stresses much better and it doesn't warp. And so we basically did a number on this part. It's definitely harder to CAD model this than it is to model their first thing, but it prints off and it doesn't warp at all. And so they just pull these off the machine now and then just print them out. And it got rid of their entire secondary manufacturing process. But that was definitely, this is a fantastic example of just sticking something in the machine and be like, doesn't work, and just, at first they were like, oh, we'll just move on. And we were like, no, wait, you can totally, a little bit upfront, more effort means you can still use this process. And so what else do I have any other photos in here of? That's another bracket that was optimized quite well. I think this was probably just done for weight, it looks like, and maybe a little bit other things, but mainly just weight. It just looks like they just threw a lattice structure along the outside surface. A lot of times, you can literally pipe the edges of a mesh, and that'll reduce the weight a lot. You don't even have to optimize it or anything like that if the goal is just weight reduction. And you're not, and of course, it depends on the part. If I'm going to go put it in a plane, I might want to actually run some FEA analysis on it and make sure it's not going to break. But if it's like a bike handlebar or something like that, maybe I don't really need that much more weight. Maybe I could literally just, if I, in Rhino, file new, no, something, and I just import a random part, like this 1-inch gear. I can literally there's actually, I'm not even going to use Grasshopper, but there's definitely a button in Grasshopper that does this. But duplicate edge, select all of those edges, and then click pipe at 0.1 millimeters. Now I've got a nice reinforced structure running along the outside of that object. And this is, of course, determined by the tessellation of my object. So if I could, I would call it basically a poor man's optimization, in that I can control the tessellation of the object through different techniques of mesh reduction or basically refining the topology. But that, a lot of times I'll see stuff that looks like that, and they'll call it topology optimization, and no, that's just you piped the edges of your mesh. But you can do that to the whole object. I could duplicate edge to the whole thing, and then hide it and go pipe at 0.1. Now this might take a second because that's a lot of pipes, but if that's what you want, or if that's an acceptable outcome, that's a really quick way of just shelling your object. Not shelling, but kind of reinforcing the exterior structure. Not saying it's the best, by no means. That's just not arbitrary triangles, but as close to arbitrary triangles as you can get. But it's not a bad way of doing it. I've seen multiple people, I don't want to say get away with doing that when they were just like, it's fine. This seemed to have met my part quality. Even reinforcing for surface deformation on really thin parts, this might totally work on that. You just need maybe a little extra structure on there, and you don't need to spend the time to write something that made a hexagonal structure on it if you were in another program, or figure out how to do it. Maybe you literally just grab all your edges and go pipe. Isn't everyone, you got a question?
And if you take tips on design and assembly for one.
Yes. So I normally, for design and assembly, I'll design parts that are printed as one assembly. I don't even put them together. Like, they come out of the printer fully assembled. And so if that's my goal. And so a lot of times it's basically just tolerancing and making sure your parts don't fuse. Like on the specific SLS machine in my office, from some experimentation, we figured out that parts fuse at under 0.4 millimeters. So like if I have anything less than 400 microns, they'll probably stick together. I should probably print them separately and stick them together if I want tighter tolerances. But like I did a lot of prosthetic arms for a while, and it was easier just to print the whole thing as one go and clean it off and give it to the client, or at least like get it all the way up until the electronics. And so like we'd pull the prosthetic arm off of the, like for instance, we'd pull the entire prosthetic arm out of the printer, clean it off, and it would be done. And so if I go here, arms, Daniel, this object prints as one piece, and it's basically a fully articulating hand that you then run some cables through, and then you can then basically use. But that's sort of one of my favorite, is the printing full assemblies. It's the more fun. I don't know if it's as useful in the real world, other than possibly prosthetics and a few other select areas. But like, it was definitely really nice not to have to actually make this. It just comes off the printer and I put some strings in it and it's done. And so that's definitely a plus. As for normal assemblies, tolerancing is important, but each printer is different, each material is different, everything is different. A lot of them will have that information set up on like accurate to 50 microns on their website or on some like user guide page. But without I would, if I was going to, the first time I basically print something I figured should be assembled, I'm expecting it to fail. I mean, I'm not that I think I'm going to get it right. Like, I would like to get it right, but I'm willing to like err on the side of like, it might not. And so, just based on slighter differences. There's also like false positives you can get occasionally. So the more accurate your machine is, which is when the SLA is fantastic for being super accurate. Like if you print it on an FDM part and it fits together and it screws really well, and like everything works, and then all of a sudden you send it off to get injection molded, like your CAD files, and they build you tools and they send it back, and it doesn't fit. It's because your FDM prints probably aren't as accurate as the injection molding tooling is from your CAD package. So maybe it gives you a false positive of it actually does fit together and screws really well, or maybe it actually doesn't fit together. And like you might think, and it might actually work if you injection molded it, but the accuracies are off. So like I know SLA is like really accurate and super useful for basically printing assemblies, because you can get different levels of, not different levels, but you can, it's the closest to injection molding, to my knowledge, that you can get basically. And so if it works in SLA, it should probably work in anything else. But I know like I've definitely printed stuff on FDM that didn't work that works in other things, and vice versa. All right. So I think that's about it.